Okay, so let's take a look at what happens with a capacitor as it is charging and after it is charged. Okay, so let's say I've got a switch right here. So right now the capacitor is uncharged. And then I throw the switch. So we're going to pretend like current is little positive charges. It's not, but that's the way that we act like it is. So what a capacitor does is it stores charge. So as the current flows, when it first starts up, the positive charge is going to build up here. That is going to repel the positive charge over here. So the current's going this way. It will repel the positive charge off this side, and the current will flow, and you'll have a negative charge on this side. So when you first start it up, from the point of view of someone, a resistor over here, it's like, hey, current's flowing, because that's what's happening. But as time passes and more charge builds up, it is harder and harder for more charge to get on here because it already has such a positive charge. So eventually the current is going to say, nope, I'm done, not flowing anymore. And then this acts like an open circuit. So if this was 4 volts, now our capacitor is charged +4 on this side compared to this side. We'll say that's 0. So if this is ground, we have +4 here. So we have +4 all the way over here, and we have 0 on this side. And now no current flows. So that's what happens. And so after it has been sitting for a long time, it acts like an open circuit. So all of the time that we're talking about is we're talking about this charging period. What is, or discharging, what is the current through the capacitor during this period while it is charging up? Because once it's charged, it's 0. So that's what we're talking about. Or if I have a charged capacitor, so it's charged, and I have a switch, so this is charged, and I have the switch, and then I close the switch. At that point, current is going to start flowing just like it did when it was charging. It's going to flow until it's completely discharged, and the current is going to get smaller and smaller. So when you look at this current through a capacitor as it is charging, the current looks like that. Well, it doesn't start at infinity. It'll start at whatever it starts at and goes to 0. So this would be while it's charging, or while it's discharging. Actually, it is still going to start at a certain amount and then go to 0. It'll go, so that this is showing the charge on it. So that's the charge on a capacitor. So Q equals CV. Also the voltage looks like that. And then as it discharges, the current looks like, so as it discharges, the charge looks like that, and so the current would look like that, I guess.
Doesn't do the opposite. I'm sorry.
It does the upside down. So So the upside down, so like right here. So this is charging, this is discharging. In both instances, they're going to 0. In absolute value, they look the same. The reason they're negative is because charging the current is going one direction, discharging the current is going the other direction. But I think perhaps what you're thinking of is this, where you have, this is the charge while it's charging, and this is the charge while discharging. Maybe? No? Okay. Okay, well, the current can't be approaching a positive number as it's discharging because the current has to be going to 0. Okay, and let's see. An inductor does something different. So let's talk about an inductor for a minute. So here's an inductor. Now, I told y'all something about a capacitor that was very important, about a capacitor voltage. What did I say?
So that it built up on the positive side and that it stopped whenever the voltage became equal to the supply voltage.
That's true. I also said something about when I said it last time on Tuesday. I also said it when we did the graphs, and I said, oh, look, it matches up here, and that's good because the voltage on a capacitor cannot change instantaneously. Do y'all remember that? Okay, but current can?
Because it can change direction.
Yeah, and it just can change. It can just change instantaneously. An inductor has the opposite. So inductor, current cannot change instantaneously. But voltage can. So the whole point of an inductor is to resist a change in current. So if it's just sitting here, and then all of a sudden you throw the switch and current starts to flow, it says, no, I don't like the current, I'm not happy about it. And when it first starts, it acts like an open circuit, and it says, no, I'm not going to let any current go through. But as the current becomes closer to a steady state, to where the current is not changing, if the current is not changing, the inductor doesn't resist it anymore. And so after a long time, the inductor acts like a short circuit.
Johnny.
What's that?
Who's Johnny? Never mind. Short circuit.
Oh, lost on me. Okay.
It's a movie. Short circuit.
I am so bad with movies. I'm just, yeah.
Well, we're probably twice your age.
Uh,
Let's go home.
let's see. Current. Let's do this one. Yeah, let's do this one. Okay. The current shown is applied to a 2 microfarad capacitor. The initial voltage on the capacitor is equal to 0. Find the charge on the capacitor at t equals 6 microseconds. So we know Q equals CV. So if we knew the voltage at 6 microseconds, we would know the charge. So at 6 microseconds, we know the voltage is the 1 over the capacitance times, and in this case, I can do from 0 to 6, because I'm not looking for a function, I'm just looking for a number of I of t dt. So this is 1 over 2 times 10 to the negative 6 times the integral from 0 to 6. So that would be that area. So that would be, the first triangle would be 1/2 times 4 times 10 to the negative 3, because these are in milliseconds, times 5, minus 1/2 times 2 times 10 to the negative 3 times 5. So, what is it?
I'm sorry.
So that is 500,000 times 2 times 5. So that's 2 times 5, that's 10, that's 5, so that's 5 times 10 to the negative 3. What, 2,500? Did you say 2.5?
2.5.
It's 2.5 times 10 to the third.
Okay.
So 2,500, unless I missed a decimal somewhere. Let's see. What number was this?
16.
It is 2,500. Okay, so then the charge is CV. C is 2 times 10 to the negative 6 times 2.5 times 10 to the third. So that's 5 times 10 to the negative third, or 0.005 coulombs, or 5 millicoulombs. All right, and that's going to be where I stop, because I'm just not really interested in doing any more.
Sorry.
Are